Hidden near the very edge of what we can observe, tucked behind a wall of closer galaxies, sits an object that has no business existing. Not because it behaves strangely, and not because it poses any danger to anything. It should not exist because, according to everything scientists thought they understood about how the universe assembled itself, there simply was not enough time for something like it to form. When the James Webb Space Telescope first turned its mirror toward the earliest few hundred million years of cosmic history, astronomers expected to find a beginning, small, messy, half-formed clumps of gas still figuring out how to become galaxies. Instead, they found something that already looked finished, a black hole so massive and so absurdly early that it does not fit inside any accepted timeline of cosmic history. And the more precisely researchers have measured it since, the worse that problem has gotten, right up through some genuinely strange new twists that only surfaced this year. To understand why this counts as a real crisis, rather than just a fun curiosity, you first need to understand exactly which rule it breaks. A black hole is not supposed to be born large. In the standard story of cosmic history, the very first black holes started out as seeds. When the earliest generation of enormous stars finally burned through their fuel and collapsed under their own weight, they left behind dense cores weighing perhaps a few hundred times the mass of our sun, small by cosmic standards, almost trivial in the grand scheme of things. From there, a black hole only has one way to grow. It feeds. Surrounding gas spirals inward, friction heats that gas to millions of degrees, and the black hole slowly, patiently packs on mass over unimaginably long stretches of time. But there is a genuine speed limit built into that feeding process, and it is not some flexible guideline. It is baked directly into physics itself. As gas falls toward a black hole, it glows so intensely that the outward pressure of its own radiation starts shoving away the very next mouthful of gas trying to fall in behind it. The harder a black hole tries to eat, the more forcefully it ends up pushing its own food away. Astronomers call this the Eddington limit, and for decades it has functioned like a built-in governor sitting on an engine, capping how quickly any black hole can realistically gain weight before choking on its own light. Run the arithmetic from there. Start with a seed weighing a few hundred suns. Feed it at the absolute fastest rate physics normally allows, with zero interruptions and zero pauses along the way. Reaching the scale of the true monsters sitting at the centers of galaxies today should require billions of uninterrupted years of steady growth. The early universe simply did not have billions of years available to hand out. The object that first cracked this story wide open carries a deceptively plain, forgettable name. Astronomers call it UHZ1. Finding it at all required borrowing a trick straight from nature itself. A massive foreground cluster of galaxies known as Abell 2744, sometimes nicknamed Pandora's Cluster, happens to sit directly between us and the deep, distant universe. Its gravity is so immense that it physically bends the fabric of space around it, warping and magnifying the light of anything unlucky enough to sit directly behind it from our point of view. The entire cluster essentially becomes an accidental lens, a telescope the size of a galaxy cluster, built entirely out of gravity and pointed straight at the dawn of time. Peering through that natural lens, the James Webb Space Telescope picked up a faint smudge of infrared light. Meanwhile, NASA's Chandra X-ray Observatory, staring at that exact same patch of sky for more than 2 straight weeks, caught something else entirely, a burst of X-rays, the unmistakable signature of superheated gas, being violently torn apart as it spirals into a black hole. 2 completely different telescopes, 2 entirely different kinds of light, one single object sitting at the center of both. That X-ray signal was so faint that Chandra should never have been able to detect it at all under normal circumstances. It only became visible because the gravitational lens amplified the light by roughly 400%. Without that lucky cosmic alignment, this discovery simply never happens. We would have no idea any of this was even out there. When researchers finally measured the distance involved, the number was staggering. Light from UHZ1 left its home galaxy roughly 470 million years after the Big Bang, and that light has been traveling for more than 13 billion years just to reach us, covering a distance of about 13.2 billion light years in the process. We are looking at this galaxy exactly as it existed when the universe was only about 3% of its current age. Sit with what that actually means for a second. We are not seeing this galaxy as it exists right now. We have absolutely no idea what it looks like today. We are looking at a photograph of the universe's infancy that took 13 billion years just to arrive in our mailbox. Then researchers weighed it, and the number that came back was even harder to explain. Estimates placed the black hole's mass somewhere between 10 million and 100 million times the mass of our sun. Not a seed, not some leftover stellar remnant. A fully grown, supermassive black hole already actively feeding, already enormous, sitting there while the rest of the universe was still figuring out how to produce its very first light. But raw size alone is not really what makes this such a deep problem. The real issue is the ratio. In the universe around us today, There's a remarkably consistent relationship between any given galaxy and the black hole sitting at its center. Add up every single star inside a typical modern galaxy, and their combined mass usually outweighs the central black hole by roughly a factor of 1,000. The black hole normally amounts to a rounding error, something like 1/10 of 1% of the total, a tiny seed buried deep inside an enormous piece of fruit. Inside UHZ1, that entire relationship collapses. The black hole is not a rounding error at all. Its mass turns out to be roughly comparable to every single star in its host galaxy combined. It is as though the seed had somehow grown to weigh as much as the entire fruit surrounding it. That mismatch is exactly why astronomers reached for a blunt, almost uncomfortable label for objects like this, calling them overmassive black holes that are simply too large for the galaxies supposedly containing them. If UHZ1 were the only object like this ever found, this whole story would amount to little more than a curious footnote, one strange outlier sitting in an already strange universe. It is nowhere close to being alone. As the James Webb Space Telescope kept scanning deeper into the young universe, it kept turning up more of them. Astronomers eventually identified an entire population of faint, tiny, deeply red points of light scattered across the early cosmos, so compact and so uniformly crimson in color that researchers nicknamed them little red dots. Formally described in a paper published in March of 2024 by astronomer Jorrit Matthey and his colleagues, these objects show up in large numbers starting around 600 million years after the Big Bang, and then largely vanish from view by roughly 1.6 billion years after it, a surprisingly narrow window in cosmic terms. By 2025, researchers had already cataloged more than 340 of them scattered across Webb's deep field images. Their spectra carry a distinctive shape, unlike almost anything else observed in the sky. Bright in ultraviolet light, bright again in optical light, but strangely dim in the narrow band sitting between those two, forming a rough V shape that immediately caught observers' attention. On top of that unusual dip, many of them show broad emission lines typically associated with gas, swirling rapidly around an active black hole, while at the same time showing conspicuously weak or entirely absent X-ray and radio emission. Exactly the kind of signal astronomers would normally expect a genuine black hole to produce. That contradiction, strong optical evidence for a black hole paired with almost no confirming X-ray signal, is part of what made this entire population so difficult to classify from the very beginning. Look closely at many of these little red dots, and you find strong evidence of a heavy black hole sitting at the center, one far heavier than its tiny host galaxy should reasonably be able to support. In the most extreme individual cases, the numbers stop sounding like careful measurements and start sounding almost like typos. Instead of a black hole representing a mere 1/10 of 1% of its galaxy's total mass, some cases show 10%, 20%, occasionally as much as 30% of the entire galaxy's mass concentrated inside that one central object. In a handful of the strangest examples on record, the central black hole appears to outweigh every single star in its galaxy combined. One additional object drives this point home with real force. A brilliant quasar catalogued as J0313-1806, shining out to us from roughly 670 million years after the Big Bang, is powered by a black hole exceeding 1.6 billion times the mass of our Sun, more than a billion suns worth of mass, fully assembled inside a universe that had barely even gotten started. At this point, the real question stopped being whether one single black hole somehow managed to grow too fast. The real question became how an entire generation of them managed to do it at the exact same time. There are a handful of possible explanations for all of this, and every single one of them would rewrite part of the accepted story of how the early universe actually built itself. The leading explanation for years has been that these black holes never began as small seeds at all. Rather than patiently waiting for a massive star to be born, live out its life, and eventually die, an enormous cloud of raw, primordial gas may have collapsed directly into a black hole in one single catastrophic event. No intermediate stellar stage required, no long waiting period. Not a modest few hundred suns to start with, but a heavy seed weighing somewhere between 10,000 and 100,000 suns. A second possibility holds that the speed limit itself is not quite as strict as physicists once assumed. Inside the dense, chaotic, gas-drenched hearts of the very first galaxies, a black hole might occasionally feed far faster than the standard Eddington rate technically allows, gorging itself in short, violent bursts that temporarily overwhelm its own outward radiation pressure and let it briefly race ahead of the clock. A theoretical study released in 2026 by researchers at Nanjing University and the University of Massachusetts built exactly this kind of model, re-examining little red dots specifically because of their unusual lack of X-ray, radio, and infrared emission, alongside their strange V-shaped spectra, and describing rare, extremely violent feeding episodes capable of pushing growth rates well past normal theoretical limits. That same model predicted something else worth noting. that the little red dots Webb has already found represent only the visible tip of a much larger population of fainter black holes currently sitting in the same violent growth phase, still hidden below Webb's current detection limits, with some destined to eventually get swallowed into larger cluster galaxies, and others left to evolve in isolation into compact dwarf galaxies or dense globular cluster-like objects. That same overmassive puzzle has also started showing up somewhere nobody initially expected. In March of 2026, a separate research team pushed this same overmassive black hole question into an entirely new arena, identifying similarly oversized black holes lurking inside small dwarf galaxies rather than only the compact little red dots Webb had already flagged. These dwarf galaxy black holes showed the same telltale absence of X-ray detections seen elsewhere in this population, leading researchers to suggest the missing X-rays likely mean the accretion process is either heavily obscured by surrounding gas or genuinely weak in X-rays for reasons not yet fully understood. Finding the same basic pattern, an oversized black hole paired with a strangely muted X-ray signal showing up in a completely different class of galaxy, suggests whatever mechanism is hiding these objects from easy detection may be considerably more widespread across the early universe than the little red dot population alone would suggest. But there is a third possibility, and this is the one that has genuinely turned this story from a settled discovery into an active, ongoing scientific argument playing out in real time this year. Astronomers cannot see these black holes directly, not even close. Every mass estimate gets inferred indirectly, based on the light coming from gas swirling around the black hole and on how fast that surrounding gas appears to be moving. Every single one of those measurements depends on a chain of underlying assumptions, and each of those assumptions has to survive an unbroken journey of 13 billion years before it ever reaches our telescopes. Over the past year, several research teams have started seriously questioning whether these particular measurements can even be trusted at such an extreme distance in the first place. That skepticism reached a genuine turning point in June of 2026, though the groundwork for it had already started earlier that same year. Back in January, astronomers at the Center for Astrophysics at Harvard and Smithsonian presented findings at a major astronomy conference in Phoenix, suggesting that at least some little red dots might actually be enormous, extremely short-lived stars, rather than black holes wrapped in gas at all, essentially a direct, observable snapshot of the exact stage where a massive star's collapse gives birth to a black hole seed. That idea offered a genuinely different way of resolving the same underlying puzzle. Not by shrinking the measured mass, but by questioning whether these objects were even proper black holes yet in the first place. Then, in June, a team led by astronomer Vasily Kokorev at the University of Texas at Austin published the most detailed spectrum ever captured of a single little red dot, an object gravitationally lensed and catalogued as Glimpse 1775, seen as it existed roughly 1.8 billion years after the Big Bang. That spectrum contained more than 40 distinct spectral lines, and every single one of them pointed toward a related but distinct conclusion from the January proposal. Rather than being simple, straightforward supermassive black holes shining out in the open or purely transitional stars, these objects appear to be young supermassive black holes wrapped inside incredibly dense cocoons of ionized gas. Inside those thick cocoons, a process called electron scattering, rather than the gas simply orbiting at extreme speed, is what broadens their light signatures so dramatically. Once researchers accounted properly for that scattering effect, the actual black hole masses implied by the data dropped by roughly 2 full orders of magnitude compared to earlier estimates, landing closer to somewhere between 100,000 and 10 million solar masses, rather than the far larger figures originally reported. Researchers have started calling this the black hole star model, and a companion study published the same month in the journal Nature reached a strikingly similar conclusion, working from a separate sample of little red dots, describing them as young supermassive black holes shrouded in dense ionized gas that had been quietly fooling earlier measurement techniques all along. That finding genuinely matters, because for roughly 4 years, plenty of astronomers had openly worried that little red dots represented a fundamental crack running straight through modern cosmology. This new spectral evidence suggests that, for at least a meaningful portion of this population, the universe was never actually broken in the way it first appeared. Our measuring instruments were simply being fooled by an unusual physical disguise nobody had previously accounted for, dense gas clouds mimicking the appearance of impossibly heavy black holes. Here's where things get genuinely complicated, though, and where the story refuses to wrap up into one tidy, satisfying conclusion. UHC-1 itself was never actually one of the little red dots swept up in that same spectral reanalysis. Its mass estimate came from a fundamentally different measurement technique entirely, built directly from Chandra's independent X-ray detection, rather than from the same broadened emission line spectroscopy driving the newer black hole star model. That means the specific reanalysis resolving many little red dot cases in June of 2026 does not automatically resolve UHZ1's own extreme mass problem in the same stroke. Its X-ray signature still points toward an actively accreting black hole holding real weight, and its position sitting right alongside its tiny host galaxy at such an early cosmic moment remains a genuine unresolved puzzle even after this year's breakthrough. In other words, part of the original overmassive black hole crisis may be quietly resolving itself as better data comes in, while another part of it, including the very object that originally kicked off this entire conversation, still stands largely unexplained. So the field currently finds itself split roughly three ways. Some objects likely represent black holes that were simply born unusually heavy from the very start through direct collapse. Some likely represent black holes that briefly broke past their theoretical speed limit during rare, violent feeding bursts. And some, quite possibly a meaningful share of the original little red dot population, may never have been quite as impossibly massive as they first appeared, once astronomers properly accounted for the dense gas clouds disguising them. Untangling exactly which explanation applies to which specific object remains one of the most actively contested questions in observational cosmology heading into the second half of this decade. And that uncertainty is precisely what keeps a discovery like UHZ1 from becoming just another entry on a list of cosmic record holders, because if objects like it are exactly as massive as the current X-ray evidence suggests, then the basic order of cosmic creation may genuinely run backward from everything astronomers originally assumed. The standard picture always had galaxies forming first, slowly gathering gas and stars, with a black hole growing up gradually inside that structure, almost like something raised patiently by a parent. But a genuinely overmassive black hole hints at the exact opposite arrangement, that the black hole itself came first, and the surrounding galaxy assembled itself around that central darkness afterward. The seed, in a very real sense, growing the fruit around itself rather than the other way around. 13 billion years ago, in a universe that had barely learned how to produce its first light, something sitting in the darkness was apparently already enormous. We only caught its shadow by pure accident, bent and magnified through the gravity of an entirely unrelated galaxy cluster, sitting right at the absolute limit of what our current instruments can detect. And even now, with sharper spectra, competing theoretical models, and a genuinely important correction to part of this story landing, just this year, astronomers still cannot fully explain how something like UHZ1 got there so early or so heavy in the first place. The James Webb Space Telescope was built to finally show us the true beginning of everything. Instead, it may be quietly proving that we never actually understood that beginning nearly as well as we thought we did. It is worth pausing on just how quickly this entire field has been forced to correct itself in real time, because that pace is unusual even by the standards of modern astrophysics. Little red dots were first noticed in Webb's very earliest images back in the summer of 2022, barely visible smudges nobody had a name for yet. Within 2 years, they had become one of the most argued over populations in the entire sky, some researchers calling them evidence of broken cosmology, others insisting they represented perfectly ordinary physics dressed up in an unfamiliar disguise. By January of 2026, teams at the Center for Astrophysics were presenting evidence that at least some of these objects might actually be enormous, short-lived stars rather than black holes at all, essentially fossilized snapshots of the exact process that gives birth to the first black hole seeds. Just months later, the June 2026 spectral analysis pushed the leading interpretation back toward black holes again, just smaller and better disguised ones than first assumed. That kind of whiplash, 3 or 4 competing explanations rising and falling within a single 4-year stretch, is exactly what real science looks like when it runs into genuinely new territory with no existing playbook to follow. What happens next largely depends on more telescope time and more gravitational accidents exactly